Okay, we are going to start the lecture. Are you there? Hello? Hello? Okay, I will start talking, and if you join, you can say that you are here. This lecture is about still soul solution. Soul solution is extremely important. We have talked about this in the undergraduate. So anybody is here? Hello?
هلا دكتور.
السلام عليكم.
السلام ورحمة الله، كيفك؟
أين البقية؟
والله ما أنا عارف، هسه بشوفهم.
لأنه الاجتماع بدأ والمحاضرة المفروض أنه بدأت أنا عم بسجل على الهواء.
على الهواء مباشرة.
أيوة على الهواء مباشرة.
إحنا اليوم أصلاً كان عندنا برزنتيشن على 4:30، بس شفاء كان النت عندها سيء وما قدرت تدخل، يعني ما قدرت تحضر، فأعتقد إنها ما بعرف إذا بتحضر ولا لا.
والبقية على كل حال أنا راح أتكلم ونعطي المحاضرة and if they join they can join while we're talking. Okay, so this is part of the soul solution. Most of the material except the very last part of it will be new, but most of it is repetition from your undergraduate. But because it's so important, I want to make sure that these ideas stay with you, because the basics are basic, whether for undergraduate, for graduate, for all soil chemistry, you need to understand them very well. So I'll go over a few things again that, and you can read in your textbook things that are related or things that I don't extend very much here. If I don't expand on them, you can read more in your textbook. So what I'll talk about is the ion activity and activity coefficients. We know, if you remember, we have talked in the undergraduate about two types of equilibrium constant. One we call the thermodynamic equilibrium constant, and the other is the conditional equilibrium constant. The conditional depends on the concentration. It's not stable and it's not a constant value, while thermodynamic equilibrium constants are constant at constant temperature and pressure. And of course, most of the reactions, I have told you many times, they are carried out at the room temperature, which is 25 Celsius or 298 Kelvin, and they are done under 1 atmospheric pressure because it's open system. So they are under 1 atmospheric pressure. So that's why whenever we see most thermodynamic equilibrium constant, they are really constant and they are available in the literature. So they are expressed in terms of activities, not concentration of the ions. Unfortunately, the activities of ions in solutions generally cannot be measured directly as opposed to their concentration. So when we measure ions in solution, we measure their concentration, never activities. Activities cannot be measured directly. So the values we obtain, whether you determine it by titration, by atomic absorption, by flame, whatever procedure you use, these are available for different ions. They will give you the concentration of these ions. But thermodynamic equilibrium constant, we need the activities. So unfortunately, the activities are not available directly. So how do we get them? We're going to concentrate and see how we obtain these activities. The activity and concentration of an ion in solution can be related, however, through the expression, the activity of B. B can be any ion. It can be cation, anion. It doesn't make any difference. That's why we say the B is any species. Species, it can be anything, ions, any ion that's in solution. The parentheses, this type, we call them, if you remember, always parentheses. So we refer to the activity of B in parentheses, and these are brackets. Brackets indicate concentration. So how do we obtain the activity? We said we cannot measure in the laboratory directly. So we measure concentration, we can, by analytical methods in the laboratory. And we need what we call gamma of B, gamma of any ion. So B, the brackets, is the concentration of species B in mole per liter. And gamma of B is the single ion activity coefficient of species B. So to obtain the activity of B, we have this, we can obtain this from measurement. Then we need this. So if we have the concentration, multiply it by the single ion activity of that species, of that ion, then we can obtain the activity. So the single ion activity coefficients are typically calculated using the extended. Why we call it the extended? Because it takes into account the size of the hydrated ions. There are equations that do not include the size of the hydrated ions. If you include the size of the hydrated ion, then that's the equation that's called the extended Debye-Hückel equation. Okay. The Debye-Hückel equation, of course, it's familiar to you, but again, I'm going to go over quickly these things. Log gamma of I, again, that's I, same as saying species B, species I, any ion. Log gamma of I, of the gamma for the single ion activity for any ion, minus A Zi square, we open big brackets, when we have this fraction I to the half, the square root of I, we'll talk about I in a minute, over 1 plus B small a sub I to the half, again the square root of I. What are these parameters in this equation? A is a constant. It has a value of 0.5 at 298 Kelvin and related to the dielectric constant of water.
الصوت قطع شوي دكتور بعد اذنك.
بقطع؟
الو
ما عم تسمع؟
قطع شوي بس هسه سامعك. كمل.
اوكي. او مرات يمكن الانترنت لما يصير خلل احكي لي. هلا ما اجى ناس لسه بعده، بس انت صح؟
بعرف.
اوكي.
هسه الدكتور هون الاي يعني بنعتمدها نص فقط لما تكون
درجه الحراره ثابته. هذه لانه حكينا unless it's said so. اذا في واحد اعطاك مثل وقال لك الحراره غير 298 كلفن and the pressure is not what atmosphere, this will change. But generally, in 99% of the cases, most of the reactions that are carried out in the laboratory, the normal reactions, they are carried at room temperature, which is this, 298 or 25 Celsius, and 1 atmospheric pressure. So that's why this value basically, and always one should know it, it's 0.5, it's a value, fixed value, constant. That's why, and it's related to the water. We almost always carry our conditions and reactions in aquatic system in water. So it's a constant value. It has the value of 0.5. B, the capital B down here, also has a value of about 0.33 at 298 Kelvin. And also, there is an O missing here, also related to the dielectric constant of water. So this is also a constant if we are given the same conditions. So that's constant A, constant B. Capital A, capital B, because we have a small a, that's different. A sub I, small a, is a parameter corresponding to size, and it has to be in angstrom. The A with the small circle above it, that's the symbol for angstrom. Angstrom is 10 to the minus 10 of a meter. 10 to the minus 10. In old chemistry, it used to be the only unit used basically in chemistry. Nowadays, with the SI system, we use the nanometer. Nanometer 10 to the minus 9.
9,
so
yes. مختلفة.
Yes, but so in this equation, always, no matter what the units that you are given A in, you have to change it to angstrom to plug it in this equation. So if you are given in nanometer, you multiply that value by 10 to change it to angstrom, because the angstrom is smaller, 10 to the minus 10. So then the number will be higher, right? Okay, so A sub I is a parameter corresponding to size in angstrom of the ion. That's why we say the extended Debye-Hückel equation, it includes a parameter about the size of the ion. There are other equations that do not include the size. So this is why this is used more, because it's preferable because of its characteristic. It does change with the change of the size of the ions. Zi, most of the time Z is similar, is the valence or charge of the ion in solution. So if you're dealing with potassium, that will be 1, calcium 2, and so on. So it's the valence of the ion. Remember, we said the ion regardless, cation, anion, it doesn't make any difference. It's an ion. So Zi is the valence or charge of the ion in solution we're interested in. I is the ionic strength. Ionic strength is related to the total electrolyte concentration in solution and is a measure of the degree of interaction between ions in solution, which in turn influences the activity of ions in solution. So what makes the concentration different from activity? Activity takes into account the interaction between all the ions that are in solution. Concentration, it doesn't matter. It's how much you have there. That's why they're two very different. And that's why we have to find gamma, because gamma takes into account that interaction between all the ions that are in solution. While the concentration is just like when we talk, say, the mass of something. Mass does not change. It doesn't matter where you are or how you measure it. It's mass, it's constant. The same with concentration. Concentration is something that depends how much of it do you have, but activity is how it behaves, how it's affected by what's around it.
Okay. دكتور هون بعد إذنك إذا أنا حكيت اللوج جاما آي وطلع عندي على اليمين رقم، إذا باخذ الأنتيلوج للرقم هذا بيطلع عندي جاما آي.
Exactly.
Okay.
This is how we do. Yeah. So and if you remember, there are examples in the book, and in the undergraduate I used to give you examples how to calculate. But now I'm just going over the principles. I mean, you can go back to the textbook. There are examples, and it'll show you how. But simple. Yeah. But remember, always never forget this negative side, so that you have a negative fraction. That way, this one will be positive, small fraction, because it would be a fraction. Because if it was 1, if gamma was 1, remember the equation we looked at a while ago, activity equals concentrations times gamma. If gamma is 1, that means activity and concentration are equal. But always the activity is less than the concentration, so it has to be a fraction. So when you find this, it's a negative, the log is negative, so this will be a fraction, less than 1 most of the time. That's the way it should be.
دكتور بعد إذنك شوف في طلبات حدا عم بفوت، لأنه الصبايا بيبعثوا كأنهم بينتظروا إنه قبول منك.
خلينا نشوف manage invite. ما أنا حطيت unmute all. I unmuted all of them. invite. المفروض إنه هم يدخلوا.
هم عم يدخلوا كأنهم في ميس عم تدخل، هاي ثريا عم تدخل
ومش مش قادرين.
مش قادرين، لا بيحكوا لي انهم بيستنوا انك انت تقبلهم.
ما انا حطيت يعني حطيت انه allow all participants. حطيت unmute all. unmute, that means they all can be here. They have to join. there is a place where you join, and if they need something, then something will pop up in front of me and I will say it's okay, but I didn't see any. The only name that appears here is you.
بدي احاول اشوف اذا بقدر اعمل لهم invite. ما داري.
Invite by email, but they should have gone through the, if they go through the e-learning.
بعرف انه هو انا حكيت لهم الاي دي هيو على الاي-learning، خذوه وادخلوا فيه.
طبعا لانه you have to go through the e-learning. You cannot join without e-learning because their names are included in that class. That means all the class will be automatically invited. Just like we did with the discussion last time. Remember, we didn't need anything.
بالضبط.
Yeah, immediately everybody showed up. And this is the ID. The ID is 923-9868-0194.
بالضبط exactly. انا هاي رجعت بعثت لهم اياه.
Yeah, but some, if they really started correctly, they didn't need this. المفروض انه automatically they go through the link of the e-learning.
المفروض يدخلهم هون مباشرة يجيبهم.
Yes, it pops in front of me something بيقول لي allow all participants. I said yes. كان في يعني إشي بسألني بس أنا already said yes.
خليني أخبرهم بعد إذنك إنهم هيك.
Okay.
بعثت لهم وبدي أشوف، مش عارف عنهم.
Yeah, في خلل.
يعني كويس إنه مسجل، يعني اللي راح إنه إشي بيقدر يشوف.
كله راح احطه على الاي-learning، بس يعني حلو انه يكونوا معنا. احنا غيرنا so that everybody will be together.
بالضبط 100%.
يعني هاي كان that was the whole point of it. How did they do it with the discussion? They went in right away. They didn't have any problem.
صحيح.
It says here, okay, ثريا admit. اوكي، هلا المفروض ثريا موجودة هلا؟
لا لسه، هي اثنين. هاي دخلت الآن.
اوكي. ثريا معنا؟
مسكر المايك اعتقد هي.
في شيء مع انه انا عامل unmute all، معناه انه everybody can be heard.
بجوز هي عامله ميوت لنفسها من تحت. في دكتور شايف
Yeah, you can mute yourself.
مش عارف. دكتور شايف هون تحت مش في شات وسكرين، شير سكرين؟
نعم.
كم قديش الرقم مبين عندك؟ 3؟
هلا هي مبينه عندنا. وهي ميس not found. One person is waiting. مين اللي waiting؟
ممكن ميس. هاي ثريا عامله ميوت هي لحالها.
هي ما هي
ثريا
عاملها unmute، بس هي لازم she has to unmute herself. هذا حكيته لكم.
عملتها دكتور.
هلا you're okay now؟
نعم.
انت ثريا صح؟
نعم دكتور.
اهلا وسهلا. finally you're on. شو اللي صار معك؟ مشكلة؟
دكتور مش عارف، بغيت ادخل الاي دي بس ما دخل.
انت كنت لازم تروحي تكبسي على اللينك اللي موجود بالاي ليرنينج.
انا بس اخذت عملت كوبي للاي دي ودخلت من التطبيق الزوم، بس ما دخل. عمل لي انه لازم الهوست يوافق او شيء هيك.
بس انا بيجيني نوت do you admit all وقلت I admit all participants يعني انا already I did that بس انت ادخلي من خلال اللينك اللي موجوده على الاي-ليرنينج اللي انا بحطها there is a link للميتنج.
تمام دكتور.
الميس بتحكي انها بتنتظر قاعده.
مين؟ ميس admit. طيب هاي انا عملت لها admission. وينها؟
هاي دخلت
اوكي. هلا ميس عم تسمعينا؟
هلا دكتور، عم اسمع.
اوكي فاينل الكل بس يمكن شفاء ما راح تقدر تجي ولا ايه؟
دكتور شفاء ما راح تقدر.
اوكي خلص يعني المهم انه موجود. طيب انا حكيت شويه بدكم نعيد المحاضره من اول ولا اللي راح عليكم؟
هلا هي مسجلة ولا شو؟ مسجلة صح دكتور؟
مسجل الجزء كله اللي حكيناه مسجل.
خلص مش مشكلة.
اوكي I was talking انه this is repetition, a lot of it so far repetition from the undergraduate soil solution, but because soil solution is extremely important I repeat certain things so that they stay with you. لأنه if you understand the basics of the soil solution, you understand soil chemistry. If you don't, you will never understand soil chemistry. So this is the Debye-Hückel equation to calculate gamma. I will go over again quickly. We're talking about the ion activity and activity coefficients. We need the activities of ions, but whether they are cations or anions, but we cannot measure them because we need them for the thermodynamic equilibrium constants. So we can measure concentrations in solution through the analytical procedures. We cannot get the activities that we need for the thermodynamic equilibrium constant. So how do we get them? So this is the relationship between the activity of any ion. It can be cation, anion. It doesn't make any difference as long as it's an ion in solution. And the brackets, this is parenthesis indicating always the activity, which is unknown. We have to calculate it. Concentration we obtain from the laboratory. So we can calculate this because we can measure it. So how do we change from concentration to activity? We have to calculate what we call gamma, or the single ion activity coefficient for every ion. This gamma, if we know gamma, multiply it by the concentration which we obtain from the laboratory, from the analysis, then we obtain activity. So basically that's what we talked about, okay? So how do we measure gamma? We use the single activity are using the Debye, what we call the extended Debye-Hückel equation. We call it extended because it has a parameter which is related to the hydrated size. We will see it in a minute. So this is what we had when you came in. So this is the Debye-Hückel equation. Log gamma of I means any species, any ion, cation, anion, doesn't make any difference as long as it's an ion in solution. Okay, and we're gonna calculate it how? Through this extended Debye-Hückel equation, minus a zi square, you open the parenthesis I to the half over 1 plus capital B small a sub I to the half. A is a constant if we have room temperature, which is 298 Kelvin or 25 Celsius, and the atmospheric pressure is 1. And most, I have told you time after time, most of the reactions that are carried out in the laboratory, they are carried out at room temperature 298. Unless they are specialized ones, then they are different and we don't treat them this way. But most of the ones we're interested in, they are carried at 298, which is the room temperature, we call room temperature, 298 Kelvin or 25 Celsius, and 1 atmospheric pressure. So if we have this temperature, this capital A is a constant. It's related to something, some characteristics of the water, and we have aqueous system most of the time. So we consider it as a constant. That's why in the undergraduate, I always used to tell you, you have to know this. It will not be given to you. This is a known value. Also capital B, it has a value of 0.33 under the same conditions. So this is a constant. This is a constant. A sub I, that's a changing one. That's the parameter which is related to the size of the ion, and it's always given in this question in angstrom. Angstrom, I was telling when Ibrahim was along, that it used to be in chemistry, the only unit used, the small unit, is angstrom. They never used nanometer and the SI system. It used to be the known unit for chemistry at the small scale. So that's why in the old equations, you find still many equations, when they derive them, the value of them in angstrom. Angstrom is 10 to the minus 10 of a meter. And most of the values you find in textbook, even in your textbooks, the A's are given in nanometer. So the first thing you need to do is always change that value to angstrom, multiply it by 10. The angstrom is smaller. This is a larger unit. So this one equals, if it's a nanometer, it will equal 10 angstrom. So we obtain this one then in angstrom. Zi is the valence or the charge of that ion we're interested in. I is the ionic strength. The ionic strength is related to the total electrolyte concentration in solution and is a measure of the degree of interaction between ions in solution, which in turn influences the activity of ions in solution. Again, before you joined, I was saying that the concentration is some value that's known. We measure it. It doesn't change. If you measure with accurate analytical procedures, that value is constant for any ion, that total ion that you have. We will see the differences later. But the activity is related to how many ions are around it, how many ions are affecting it to change from concentration to a value which is different. We call the activity. So that's why gamma, with a negative sign here, it will be always a negative fraction, a negative value, to give you a fraction, to give you less than 1. If it was 1, remember, activity of B or I or whatever equals concentration of B times gamma. If gamma was 1, that means activity and concentration are equal, but that's never the case. So gamma is usually a fraction less than 1, so that activity is less than concentration. So that's why the value here is negative. Never forget, when you calculate, if you miss this negative, all your calculations will be wrong. So extremely important. الواحد دائما ينتبه minus.
Yes.
Okay. Okay, the ionic strength, this is the one in the equation. How do we get it? I, command, this is repetition, but we just go over it again. I equals half summation of Ci, which is the concentration of each individual ion, multiplied by the square of the charge of that ion. So if you have, say, 10 different ions, each one of them, you put half first and open big bracket, and you take the concentration of each one of them, multiply it by the square of its charge, then you add to it the next concentration of the next one, multiply by the square of its valence, and so on. You add them all, and remember, there is a half in front of all this. Half, and you open the big parentheses or brackets to calculate this. So that's I, the ionic strength. Ci is the concentration in mole per liter of the ith species. I, B, whatever, you know, that means to cover all the ions in solution. Z, the same thing, whenever we see is the charge or valence of the ith species, just like the one in the Debye-Hückel equation. And summation sigma, you know it in math, that means you extend or you sum over all the values. Okay. Now, we reach this so that we eventually come to this important thing. الأصوات من عندكم ولا من عندي؟
أنا عامل ميوت.
في شيء يعني ناس بيحرك شيء أو شيء، على كل حال يعني في أصوات عم بتبين عندي. Okay, the ion activity product. This is very important. Why we were interested in the gamma, calculate activity so that we see how the products, how the compounds that precipitate in the soil, how they behave. How do we know what's happening in the soil system? So the ion activity product, this is what we're going to talk about after now we know what activity is. For the dissolution reaction of the solid MALB, just like any cation, anion, you know that how we write a compound, solid. So it dissolves into A of M. We're considering that the valence of that M is M plus. That's how many charges it has. M could be divalent, trivalent, whatever. Aqueous to indicate in solution, in aqueous system, plus B of L, the capital L is the species here, and the negative charge of it is small l minus, again, aqueous. The ion activity product, IAP, we abbreviate it from ion activity product, IAP, is defined as M to the M plus multiplied by A, remember the stoichiometric of that, and multiplied by L, the activity of L, with the charge L minus, raised to the power B, which is its stoichiometric value. Now, where the solid, if you notice, the solid disappeared, right? We usually have this times this over the solid. But if you remember, we said pure solids always have activity of 1. Pure means pure in structure, not pure from outside impurities. No, we talk about the compound pure in its structure. No other atoms are inside except the M and L in that compound. So the ion activity product, IAP, is defined as M to the power of M plus, which is the charge of it. And the A is, remember, the stoichiometric, just like any other compound you write. Let's take example to make it simpler. For gypsum, Ca divalent times sulfate, divalent again, this is negative, this is positive. And the sulfate, calcium sulfate, which should be under it, is 1, activity 1, so it disappears. So that's why we call it the ion activity product, because the activity of the solid disappears. So we have only multiplication of the activities of the ions that form that compound. So for gypsum, it's formed of calcium and sulfate. This is very important. Why also we need the IAP? What do we need to know about this? Why do we calculate it? IAP, the ion activity product, can be applied regardless of whether the dissolution reaction is actually at equilibrium or not. So suppose we have gypsum. We suspect gypsum to be in the soil system. So we're going to find out, do we have equilibrium? And how can you have equilibrium? You have to have the ions and the solid at the same time in the same system. You cannot have ions alone without solid and you say, I have equilibrium. No way. So you have to have the ions, but you can have the ions and you don't have the compound, the solid compound. What does that mean? So that's what we are gonna, that's why we use the IAP. It can be applied regardless. That means whether you have equilibrium or not, I can calculate this. And of course, now, if I ask one of you, how do we calculate this? Do you know? From what I already said. Now, what are the parentheses we said?
Concentration.
These are activities.
Activities.
Activities. Concentration bracket.
Yeah.
So, but I don't have this. How do I get the activity of, say, calcium? Somebody's talking. I can't understand. Whoever is talking, I cannot understand you at all. So we have calcium, remember, from the concentration we measure, we go through the calculation, we calculate I, the ionic strength of that solution, then we calculate gamma of calcium, remember, gamma, the single ion activity, multiply it by the concentration we obtain from the laboratory, then we obtain the activity of calcium. We do the same thing for sulfate. For every ion, then we multiply them like this to get the IAP. That's why we can apply it regardless. As long as we can measure calcium, we can measure sulfate, and we can measure all the ions. We can calculate gamma for calcium, gamma for sulfate. So we multiply them by each other. We have the IAP, the ion activity product for that particular compound. So why also we use it? IAP can be used for determining whether the solution equilibrium actually has been achieved or not. So this calculation, we can tell whether we have equilibrium or not, or what do we have? We measure what we call the relative saturation, omega. Omega is the relative saturation. We will see why we call it that. What is omega? IAP that we calculate at any time. Remember, we can calculate in any solution we collect from soil. We can calculate this through the procedure I have told you. So now we have a value. That's IAP. K, solubility product, or K of equilibrium for that solubility, is a constant. This is the equilibrium thermodynamic constant which we obtain. It has a known value. We obtain it from the literature. So this is known. This is not known. This is at any time I bring a sample, calculate, and multiply this, we obtain this value. So, and we divide this value we calculated over K, which is known, okay? Then we get omega. If omega is less than 1, if we divided IAP over K and we obtain a value less than 1, what does that mean? That we say the solution is undersaturated. What does it mean? If this value is smaller than K, that means we do not have enough calcium and sulfate to give you equilibrium. Less than K, that means these values are still, we have them both, but we don't have enough for this compound to start precipitating. We do not have equilibrium. So we say this solution is undersaturated. It did not reach the saturation or precipitation point. Understand it?
Yes.
If omega is greater than 1, if we calculated IAP and divided it by K, then we got a value. شو هالأصوات؟ أصوات ناس عم بيحاول يحكي ولا؟
لا في اتوقع يعني الصوت من عندك نفسه دكتور.
من عندي أنا؟
لأنه إحنا كلنا عاملين ميوت.
أوكي.
ممكن المايك أو إشي ممكن بيرجع
لا
الصوت.
ما له العادي لما أنا أسجل محاضرات ما عمري سمعت إشي هيك.
مو هاي تعتبر لايف دكتور، بتفرق يعني عن التسجيل العادي.
ممكن لأنه في ناس ثانيين على الخط. طيب. So if omega is greater than 1, we divided IAP. After we calculated it, again the normal procedure of calculating it, we obtained that value. We divided by K, and we found this omega greater than 1. So what does it say? When I multiply this by this, it gave us more than K, and this cannot be allowed. So that means the precipitation will start to reduce the amount so that we have equilibrium. That's why we say supersaturated. Super, that means above the value that we need for the precipitation. So precipitation starts to reduce because at the end, the only thing that will last is equilibrium. If we have less, that means we do not have enough. We will never have the compound anyway. If you have more, it cannot stay. Some of these will combine together, will form a precipitate, will precipitate, and this will be reduced until this and this are equal. So that's why if you have supersaturated, it will not last. These will combine together, precipitate to form the compound until we get equilibrium, when it's omega equals 1. If omega equals 1, this and this are equal, so that means we are at equilibrium. We multiply these They gave us the same value as K. That's equilibrium. Nothing will change, nothing will happen. Okay, now again, why do we this? We want to see, our interest is to know any ion, what are the species or the different chemical forms it's in. So you remember we called it speciation. Find all the species, all the different forms of any ion. مثلا we take calcium. This calcium, what's there? What's there? Calcium, what's combined with? What are the different species that calcium is involved with? So that's speciation. Total ion concentration, which is the sum, total ion concentration, the sum of the free and complex ions. When you measure an ion, any ion, calcium, potassium, nitrate, sulfate, any ion you measure, which, sorry, you measure in the laboratory, that value you obtain, it does not differentiate between the free ion, say calcium, and all calcium that's involved with ion pairs, with complexes. It does not differentiate, so it gives you the total. So that's why we need, how do we find the different species? The total ion concentration is what we get from the laboratory. It involves everything. So it's measured by analytical techniques and provides information. What do we understand? Why do we do this total? It gives us quantities of ions available for plant uptake. Plants will take the single ion. The minute they take a single ion, some of the complexes will form, change, and give you the single ion again. And equilibria, every one of them goes into certain equilibrium. So anything that's in solution, the plants eventually will utilize. Also the movement through the salt profile, these are all ions. So it will give you how mobile it is, how much it moves in the salt solution, it goes downward. It is important that the speciation of chemical forms of the free and complex be known. We have to know. Ions in salt solution can form a number of species due to hydrolysis, complexation, and redox reaction. We'll take an example of a general hydrolysis reaction. Of course, this can be, say, aluminum going into ALOH, so on. Any M is the metal, so that it's a general thing. You can apply it to any multivalent ion in solution. This is water of hydration. Many of the ions, remember, are surrounded by water of hydration. They are water molecules surrounding that metal or ion. And the X indicates the number of the H2O molecules surrounded. And it's generally the same as its coordination number. If you remember in the undergraduate, we talked about the coordination number of ions. So this is related many times to the number of the coordination of this ion. So this is variable, H2, how many water molecules will surround it. But remember, H2O water molecule, it does not change the valence of it. These are molecules. So how does hydrolysis? Hydrolysis, that means this one, M, will react with water to take part of it. Because it's cation, of course, it's going to react with hydroxide ions. It will take hydroxide. So the M, now it has OH. How many of them? Y. Y can be 1, 2, 3, depending on the type of ion and the number of the reaction process that took place. So instead of, remember, M, it has only water molecules around it. Now M, it attached to hydroxide ions. The number of those ions, Y. Of course, if X, remember I told you it's the coordination number fixed basically for many ions. So we are subtracting from X how many OH were surrounding M. You have a question?
لا جاوبنا.
So M, now it has Y OHs, and since the total number of H2O was X, so we have to subtract that Y from X. So the number of water molecules that remain, because these are fixed positions, coordination numbers, certain known number of H2O surrounding this M. If one OH takes the place of H2O, you subtract that. Less H2O molecules will be surrounding. So if there are OHY of them connected with M, you subtract that Y from X, the original one. So the H2O molecules will be X minus Y. You understand what I'm saying? Simple. Okay, now, the valence of it was N plus, but each OH that attached to this M has one negative value, right? OH minus. So we have to subtract. Now, the N minus Y, because each one of these Y's is a negative one, so you subtract it, just simple number. N minus Y is the new valence of this complex. N was the original. Water molecules are neutral. So that's the same valence. Say if it was aluminum, this will be 3 plus. If took H2O, say 1, so this will be X minus 1, 3 minus 1, say, and the valence will be again N, which was 3 minus 1. So you apply whatever the valence, the actual thing for the ion that you're interested in. Plus, if Y OHs got attached to M, reacted with M, where do they come from? H2O molecules. So for each OH that was attached to M, you have to have a hydrogen released. So the same number of the hydroxyls here that were reacting with M, there will be the same number of H plus released from the water molecules. Splitting, that's what hydrolysis is, the splitting of the water molecule. OH attached to the anion, to the cation, and H becomes in solution. That's why many of these cations that hydrolyze like that will give you acidic solutions, because of they take the OH and they release the H, so the solution becomes more and more acidic. Good? Clear everything?
تمام ممتاز. عارفينها هاي دكتور، احنا برضه اخذناها.
طبعا, yeah, but I'm just repeating because it's very important for you to know this.
أكيد.
Okay. So, analytically, it is not possible to determine all the individual ion species that can occur in solid. It's impossible. Not possible. مش معنى انه hard or difficult. No, we can never determine the different species, because remember, the total concentrations gives you everything. Even if you have 10 different species of calcium, when you measure calcium in solution in the laboratory, you get the total concentration of all of them together. So individually, we cannot measure them, not possible to determine the individual ion species. So what we write, what we call a mass balance equation for the total concentration of a metal, MT total of N plus the value of the valence of it is N, like we have seen in previous example. So M total, the total, is each equals, actually this should not be N plus, because we don't have to put N, because here it gives you everything. So you don't have really to put the N plus here. You should say just M total. It should be, it's here. It's by mistake I wrote the N plus. You shouldn't have the MT total, but this is to indicate what ion we're interested in. So this is the free ion, nothing connected to it, plus ML. The ML is the concentration of the metal ion associated with the remaining metal ligand complexes. So we will see an example, say, of calcium in a minute. So these are all the complexes, and this is the free ion. All of them together gives you the total. That's what you obtain in concentrations. So if we take calcium as an example, calculation of the concentration of the different calcium species present in a typical soil solution from a basic soil, calcareous soil like in Jordan. Assume that calcium exists only as free hydrated calcium ions and as complexes with the inorganic ligands, carbonate, sulfate, chloride. Assume. This is to simplify things. Of course, it's never the case, but suppose we have the most important ones, carbonate, sulfate, chloride, anions. that will combine or complex with calcium. So what are the complexes that will form? So we have CaCO3. Remember, we name this, and you should know it. We call this ion pair. We put the 0 to indicate it's not the solid calcium carbonate. This is an ion. Calcium got complexed with carbonate ion, which is divalent. Remember, divalent, but it's 2 negative. So it gives you CaCO3 0 valence. So that's an ion pair. Then with the, where did this come from? Remember, we said carbonate, sulfate, chloride. Where did the bicarbonate? This is bicarbonate, CaHCO3 plus. Any one of you can tell me where did the bicarbonate come from? No? Okay.
CO2, H2O.
Ca, where does, remember, we said assume we have only 3 ligands: carbonate, sulfate, this is CO3 2 minus, sulfate 2 minus, Cl 1 minus. Now, when we wrote the complexes, we wrote CaCO3, but also we wrote CaHCO3. It's not mentioned here, right? Plus CaSO4 ion pair, plus CaCl. This we know. This we know. They're here. Chloride we know. Where did this one come from? We didn't mention it here, but automatically, if you see carbonate, always, it will hydrolyze and will give you bicarbonate. Remember, this is negative. We looked at the hydrolysis a minute ago, and it was a cation, so it took the OH. This one, because it's negative, it takes hydrogen from the water. So it forms immediately, you will have the carbonate and the bicarbonate, CaCO3 plus H from the water to give you HCO3 -1. -1 and divalent calcium will give you the complex +1 charge. You understand? So even if you're not told, if you're given these and you miss writing this, you miss something. You should know. That's why this is automatic. Any good chemist, any salt chemist, any good, immediately they know that if you have carbonate, you are going to have bicarbonate automatically with it. They don't have to tell you. So that's why it's not given here. But you cannot write the complexes without writing the bicarbonate complex that comes from the hydrolysis of the carbonate in solution. And then the calcium sulfate ion pair plus the CaCl pair or complex. So the Ca total can be expressed as the sum of free, and this is all very detailed in your textbook, but I'm just going through the major things so that you, when you read it one day and when you need it, you know how to read it carefully. Ca total equals the free ion. Remember, a while ago we said the free ion M plus, Mn plus, this is it, calcium free. Then the calcium carbonate here, ion pair, the calcium bicarbonate complex, the calcium sulfate ion pair, and the calcium chloride. All of them. And of course, if you have some others, if you have phosphate, this, you add them. We simplified the problem because here we said assume we have only these. But in reality, you bring in a salt solution, you calculate, you determine all what it has, and you write a full equation. Here you add all the rest of the complexes that exist. But here to simplify, we said we will look at only 3 of them. Okay, this is the new thing. Now, in your book, it mentions that so many now procedures that are, yes?
الصوت قطع دكتور.
هلا أحسن؟
قبل شوي قطع. هسه تمام سامعين.
Okay. In your textbook, always they tell you there are so many computer programs to calculate this speciation for you. I want to show you how the old people in the decade, the time like when I studied, when I got my PhD at that time, and the older scientists, how they used to go through these calculations for days and days and days and months. Nowadays, you put them in computer, you push a button, that's it. You get it in a few seconds. The steps that you do this really is very intriguing. So I want to tell you how even the computer, what goes inside the computer for these calculations. So the procedure for, sorry, I by mistake sometime I touch the thing and it lowers the upper thing without knowing. Procedure for correcting the measured ionic concentrations to actual concentration activities. How do we do the speciation in reality if we don't have computers, programs like we do have now? Step 1, ionic strength measured ionic concentrations are assumed to be actual ionic concentrations. Remember when we said, when you measure, say, calcium, it gives you in the laboratory the total. It gives you calcium plus all the other species with it. In the first case, we're going to assume what you get is only calcium. You measured calcium total, we'll assume that's only calcium. So we measured ionic concentration are assumed to be the actual ionic concentration. Step 2, activity coefficient. If we have all the ionic concentrations, we can calculate ionic strength, right? We saw the equation. That's why I went through the equations. You say I equals summation of half summation of you. We saw the equation. So from this ionic concentration, you calculate ionic strength. Now, if I have ionic strength, I go to Debye-Hückel equation and I can find activity coefficient, single ion activity. Gamma, remember for gamma, you needed ionic strength. Now we have ionic strength. Calculate the single ion activity coefficient. Calculating using ionic strength from step 1. So now we have ionic activities. How do we calculate them? The concentration we assumed times gamma that we calculated. So we get the first ion activity for that ion. You understand? You're keeping up with me? Are you
Yes.
keeping up with me? Concentrate, simple, but we will keep repeating the same. Your mind has to concentrate on the different steps we are doing. Now, the ion pair concentration, the calculated using ionic activities we have. We already calculated ionic activities in this step. We use these and we get the ion pair dissociation constants are available. This is from the literature. If I have the K and I have activities, then I can calculate how much do I have of that ion pair or complex. Say, remember, like CaSO4, CaSO3, CaCl. Any of those, now I know how much I have. Understand? Keep up with me. So we calculated ionic strength. From the ionic strength, we calculated gammas. From gammas, we calculated activities. We have the activities from the ion pair dissociation constants. Now we have ion pair concentrations, initial ones. So we calculate them using the ionic activities from step 2 and ion pair dissociation constants from the literature. Now, if we have ion pair dissociation constant, now we have ion pair concentrations. Remember the first one, we assumed the ionic concentration is the total thing we obtain, but now we have ion pair concentration. So we subtract those from the concentration we obtain in the laboratory to correct. We have a newer value. So we subtract from this, okay, calculated using ionic activity from, we said this, step 4, revised ionic strength. A second estimate of ionic concentration is made by subtracting the first estimate of ion pair concentration from the measured concentration which we obtained from the laboratory. Okay, the next, if I have a new concentrations now, new different species, I calculate a revised new ionic strength will be closer to reality. The ionic concentrations from step 4 are used to calculate a second estimate of ionic strength. Then step 6, revised ionic activities. New activity coefficients are calculated based on the new ionic strength. We calculate new gammas. Calculating new gammas, we calculate new activities, okay, using the revised value of ionic strength. The new activities are calculated using the second estimate of ionic concentration from step 4. Okay, and the last, then we subtract again and we get revised ion pair concentrations. The ion pair concentrations are estimated a second time with the new activity values. And so we keep on. Steps 2, 3, and 4 are repeated and repeated and repeated until when you add all these species you obtained, they have to be equal to the total concentration you actually obtained from the laboratory analysis. Then you say, oh, my work is correct. My values are correct. If they don't match, you keep on. Sometimes you have to do this 10 times or more. It's a very, very tedious procedure. And so the last thing, that's what they call the iterative or trial and error or repetitive assumptions or repetitive approximations. It has many different names. Successive approximations, you keep doing it and then you put the mass balance equations into this algebraic way. That's what the computers do. Ca total from the lab, this value we know. Okay, so we have calcium plus 1. These are, if you go back to your book, you will find K1 conditional, K2 conditional for the formation of all these pairs. Okay, so the free ion concentrations obtained from the iterative approach can then be used to calculate the concentrations of the metal ligand complexes. So we finish this lecture, and the last part soon, I will start a new and your final thing, which is the carbonate system, very important for you to understand the calcareous soil system and how we obtain a value for a known pH value for calcareous soils. We'll go through it has a lot of math and chemistry, interesting, but hopefully we'll go through it slow and you will understand it. If you want any discussion period about your project and thing, we can have another session just for that. You can tell me, you can send me an email, you agree, and we decide and we can talk about that. Good?
يعطيك العافية دكتور.
يعطيك العافية دكتور، ما قصرت.
Do you have any questions ولا خلصنا هيك؟
لا thank you، ما قصرت.
Okay, if you need any discussion, like I said, send me an email. We will set up like we did last time, and we can talk about the project and how far you're going and what problems you're facing.
إن شاء الله.
Okay, يلا الله معكم، مع السلامة.
يعطيك العافية
دكتور.
الله يعافيكم، مع السلامة.
هلا الله معك.
مع السلامة.